Okay, so we're talking about heaps. Go ahead and take a look at this binary tree that you see here. Basically, the definition of a heap is super, super simple. It's just every node in the tree is larger than either of its children. Okay, what that means is, so if the 35 is going to be bigger than any of the nodes in its subtrees, just so that last sentence was basically like a corollary of what I said at first, right? So first, the definition that I gave you was for every node in the tree, it is greater than either of its children. But if you think about it, if that's the case, then you can also say that every node in the tree is bigger than any of its descendants. Right? Okay. So that's the definition of a heap. Turns out that there's a lot of things that become very simple when we it's very easy to do when we start with that definition. The only other thing I'll say about a heap is the way that it is structured is always going to be so that the tree is, and now let me just say, all of the levels will be full except for the bottom level, and the bottom level will be filled in from left to right. There's probably a word for that we learned, but I get a little confused because every textbook that I read gives it slightly different definitions for these things. So I'm just going to do the definition from scratch. I think maybe complete binary tree. Yeah, I think a heap is a complete binary tree. I think that's right. But you get the idea, right? It's always going to be all the levels are full except the bottom one, and the bottom one is filled up from left to right. Okay. Okay, so turns out, I always struggle at this point with, I think I just want to give you a little sneak preview about what the implementation is going to look like, because the implementation turns out to be the cool part of this. Because a heap is always has this attribute of being complete, we're going to call it complete. It's very easy to store it in an array. You just store, so the way that the array would look is the 0 element would be 45, the next element would be 35, the next element would be 23, the next element's 27, the next element's 21, and so on. So if I were to take a look at the array that is implementing this heap, it would go 45, 35, 23, 27, 21, 22, 4, 19, 5. And then it turns out, and we'll look at this a little bit later, but it turns out that it's very easy to find a node's children or parent just by doing a little math. Find the index of a node's children or parents just by doing a very little math. But we'll get there in a minute. I just think that it's, when I'm talking about inserting and removing nodes from a heap, I always want to reference the fact that the array is how it's being implemented. It just kind of helps in the conversation. Okay. All right. Let's talk about how I would insert something into a heap. The way I'm going to do that is I'm going to start by inserting it. Well, even in order to make sure this is a heap, I'm going to have to insert it right next to the 5 down here as 21's left child, right? And it turns out that in your array implementation, that's just, if the name of the array is items, that's items sub num items. That makes sense? Okay. So very easy. I'm just going to start off, but let's say I want to insert a 42 into my heap. I'm going to start off by just saying items sub num items gets 42. And that will put the 42 down here like this. Okay. Then what I'm going to do is I'm going to move the 42 up the tree until it gets into the correct position by swapping. Okay. In Zybooks, they call that percolate. I learned it as re-heapify up. So anyway, so if you hear me say re-heapify up, you'll know what I mean. I guess I should try to use the word percolate. So we're going to swap the 42 up until it gets to a place where its parent is bigger than it. Right? So I'm going to swap the 42 and the 21. 35 is still less than 42, so I'm going to swap the 42 and the 35. Ooh, that's not what I wanted. Right? And then the 45 is bigger than the 42, so I'm done. I'm back to having a heap. Okay? So what's the big O for insertion into a heap?
Looks like log n.
Sammy, I think if you're trying to talk, we aren't hearing you. And I
Ouch.
don't know why, but you may have to just use the chat. Oh, so yeah, there's something about the speakers in here. Although I don't know why my laptop wouldn't be working for that, but it says huh. Anyway, I apologize. You will have to use the chat if you want to say something to us, I guess.
Oh, it said log in.
Yeah, log in. That's correct. Yeah, it's going to be big O log in because however many levels there are here, that's the maximum number of swaps you're going to have, right? And with this heap setup, we don't have the problem of possibly deteriorating into n, right? That we had with a binary search tree, because we always know. In fact, it's not even going to be just big O log n. It's going to be exactly log base 2 of n. Well, except it might not have to go all the way to the top, I guess. But the absolute maximum would be big O log n. Whereas even I remember even in an AVL tree, there was something about it could be as bad as 1.5 times log of n, right? Okay, so let's talk about removing an item from a heap. The thing about remove with a heap, there's Sammy. So the thing about remove from a heap is that we're limited to when we remove something from a heap, it's always the biggest item. So we only ever remove the root of the heap. Okay, so the place where this really comes in handy is a priority queue, right? Typically, what we're going to want to use to implement a priority queue is a heap. It does exactly what we want it to. So removing from a heap, that means I'm going to remove the 45. But the other thing I want to observe about that is that I'm going to end up without this 21 node down here, right? Because if I have to remove a node from this, the one that's going to get taken away is the last one. Otherwise, it's not a heap anymore. With me on that? So I need to make it remain a complete tree. So in order to do that, however I get there, when I'm done removing the 45, this node right here that currently has a 21 in it is going to be gone. Right? So what I'm going to do is I'm going to replace the 45 with whatever's in this last node. And then how do I actually get rid of this node so it's no longer in the tree? What's the actual C++ code for that? It's like, if you're really in tune with like how the array is going to be implementing this thing, the 21's in the last position of the part of the array that's being used.
Move it forward.
Well, we're just so the C++ code for this would be num items minus minus.
Right.
Make sense? Okay. Okay. So we're just saying we have one less item in the heap. Okay. So we're gonna put the 21 up here where the 45 is, and we're gonna say num items minus minus. So we remove from the heap. So this diagram, the only difference is I circled the 45, right? Same thing again, right? So, but this time the 21 is highlighted. I don't know if you can even tell that. So we put the 21 at the top, and the last element in the last level has been moved to the root. So what I was going to say is we move the 21 to the root, and also we get rid of that last node. Okay. Now what do we have to do? Fix the tree. I think this is why I like the reheapify, right? So what I have to do now actually is reheapify down, right? And I don't think, I could be wrong about this, but I don't think Zybooks actually has a term for that. They just call it fix the heap, right? But so reheapify down means take the 21, take the root, swap it with the larger of its two children. Did you catch that? Swap the 21 and the 42. And then keep doing that until you get to a place where either you're a leaf or you are already bigger than both of your children. Right? So in this case, the 21 is going to get swapped with the larger of his two children, which is the 35. Okay. Big O for removing an item from a heap. Yeah, log in. Worst case, log in. Because I'm going to have to, at the worst case, I'm going to be hitting each of these levels once. Okay. Any questions about removing and inserting? That's basically like 90% of what you need to know right there. Kind of a nice break after AVL trees and black and red trees, right? What I want to do next, so basically there's two more things I want to do, kind of two and a half, I guess, but I just want to sort of go through the Zybooks material just to make sure there's not like details that I skipped over, so I'm filling any gaps. And then we want to talk about heap sort. And so what do I want to do here? Let me bring up Zybooks. Okay. So heap concept, this is just the definition, right? Every node is bigger than its two children. Fair enough. Oh, by the way, one thing I didn't mention is that you can have a max heap or a min heap. Everything that I just did was about max heaps, meaning that, so a max heap is where, like I said, every node is bigger than its two children. A min heap is just the opposite, right? Every node is smaller than its two children. So Is this a max heap? There's 60, right? Everything else is fine. So I guess one of the main points of these exercises here, and sometimes students miss this, is that the items down here in each level can be in any order. The order doesn't matter. It's not like a binary search tree where smaller things tend to be on the left, right? And so I've got some numbers down here in the, I don't know if this is the third level or the second level. Level 2, level 0, level 1, level 2, right? So I've got some nodes down here in level 2 that are bigger than nodes in level 1, and that's okay. A max heaps root must have the maximum key. True or false?
Yes.
True. Right. Okay. So here's our insert and remove operations. They're going to call it percolating. This is pretty much just repeating what we just did, right? We're inserting an 85, so we put it down at the bottom. Actually, let's just go through this real quick. Here's the starting tree. I'm adding an 85. So I put it down here as the last node in the heap. Then I percolate it up. Okay. And it stops there because the 88 is already bigger than. Oh, so now we're removing the root. Okay. We take the 88 out. We put the 80 up there. And then we percolate down. Do they call it? Percolate node down. Yeah. So percolate up or percolate down. Okay. Stop me if you want me to slow down. If you have any questions. I think we're just going over the same stuff again. The height of a max heap is always log n. Worst case complexity of insert is big O log n. Removing is big O log n. Let's just double check and make sure there's nothing tricky going on here. Okay. Min heap, same thing, just smaller on top instead of larger on top. I think I can skip over this. Select all the valid max heaps, obviously not B. Is A valid? No, the 25, right? Is C valid? No, the 29. Oh, and the 13.
Wasn't the shape not valid either?
Oh, yeah, good point. Good point. Right. This 96 would have to be over here as 42's right child.
Yeah.
Looks like D is valid, yeah, but it's the only one. Okay. Okay. Now we get to see a little bit about how these are implemented. So here's a heap. Here is the corresponding array. And I like how they are shading these in here because you can see here's level 0, the salmon color or whatever that is level 1. The gray color is level 2. Okay, so if I give you an index and I ask you what is the left child, what is the index of that node's left child? How can you do that? So in the case of 72, that I keep getting hung up on how to say this. The index of that node's left child would be 1, right? If I'm talking about the index 1, the index of that node's left child would be 3. 0 goes to 1, 1 goes to 3. 63, the index would be 5, 2 goes to 5. And that's all we can do in here. So I'm not sure if that gives you enough or not, but 0 goes to 1, 1 goes to 3, 2 goes to 5.
3 would go to 7.
3 would go to 7, right?
So you're like adding the power of two?
It's not a power, actually. It turns out to be just a multiply by 2. Multiply by 2, add 1. What about the right child? Should be able to get this. Yeah. Just 1 over, right? Multiply by 2, add 2. And then parent, divide by 2. And I think it actually turns out to be, so 1 divided by 2 is 0. 2 divided by 2 is 1. So it would actually turn out to be n minus 1 divided by 2, I think. Make sense? So 3 minus 1 is 2, divided by 2 is 1. 4 minus 1 divided by 2 is 3, divided by 2 is 1. So the parent of 16 is 58. Okay, so pretty simple formula for how to figure out children and parents. That's really the main thing that you need to know about this. In your homework, I'm going to have you trace through the heap sort, just the same way that I had you trace through all those other heaps before. I don't know if you hated that or not, but and what I'm going to have you do is actually for each step, draw both of these pictures. So you can see the tree and you can see how it's being stored. Okay, and we'll do that in a second, actually. Maybe I need to just move on. I think we've already covered most of this now.
Conceptually, I'm having a hard time wrapping my head around a tree and an array at the same time. Is it just because we're just doing the multiply plus 1 that's where we get the tree form of it, or like?
So that's a good question. I mean, basically what we're saying here is that, okay, here's the abstract concept.
Okay.
We want to be able to think of this as a tree. We could implement that using pointers and nodes with a left child and a right child. We could do that. Right. That would be one implementation of that abstract concept. But it turns out to be a lot simpler to just implement it using an array.
Okay, I think that
helps at least.
Yeah, it definitely
okay.
Helps.
He's not giving this author is not giving the formula just yet. Match each max heap to the corresponding storage array. I think in the interest of time, I'll just let you do that. I think you pretty much got the hang of it. Parent and child indices. Here they're actually going through the algebra process of making a table, X and Y, right? So the formula for parent is I minus 1 divided by 2. Children are 2 times I plus 1 or 2 times I plus 2. Okay. I'll let you do this on your own. Here's the percolate algorithm. So remember, percolate up was starting with the node that is being percolated, compare it with its parent, and swap up if it is less than its parent. That in a while loop, right? So while node index is greater than 0, so while the index is not the root, while the node we are considering is not the root, here's just using the formula to find out what the parent of that node is. If that node is less than that node's parent, we're done. Otherwise, swap the node with the parent, set node index to the parent index, and go again. Okay. Percolate down. A little more code, right? Let's see if we can work it out here. So left child, And then value is just so I don't have to keep saying heap array of node index, I guess, right? So this is the value of the current node. While the child index is less than array size, so we're going the opposite direction, right? Instead of while index is greater than 0, we're saying while it's less than the array size. So we're starting at the root and going to the leaves. Find the max among the node and all the node's children. Okay, so max value gets the node's value. And then this, I'm not sure this is the way I would write it, but I've got a for loop going up to, but it also stops if I hit array size, right? So the reason I need this is in case the node we're looking at has a left child, but not a right child, right? So keep going, keep doing this loop as long as I is less than 2. So I'm going to do it for I equals 0, and I'm going to do it for I equals 1. But I'm not going to do it for I equals 1 if I'm at the end of the array. This doesn't seem like the clearest way to write that to me, but I wouldn't use a for loop. Anyway, not that I've written it recently, but it's okay. So what we're going to do is we're going to say, we're just figuring out what the maximum value is and what the index of that maximum value is between the parent and the parent's 2 children, right? That's what this for loop does. If the maximum value is the same as the value of the node, that means we're done. Otherwise, swap the current node with the child that has the highest value. Move node index down to that new node, and then figure out its child index. Okay. Okay. I probably went over that in more detail even than you really. I'm really all that concerned that you understand this in, but that's okay. Heaps using arrays, just some exercises I will let you do. 10.3 is exactly what we just did, except using C++ instead of pseudocode. So I'm not going to go over that again. Insert and remove. Okay, so the next thing we're going to talk about is heap sort. I think I think I'm just going to do this with using my own diagram. So I'm done with Zybooks for now. However, I need to take a 3-minute break. So let me pause. So basically what we're going to do for heap sort is we're going to start with an array just filled with numbers that are not necessarily sorted. And we're going to think of this array as if it were a heap, just as sort of a tricky way to get those numbers sorted. Make sense, basically? So I'm going to think of it as a heap. The first step in heap sort is going to be to change this thing into a heap. That actually turns out to be half the battle right there. Once you've got it as a heap, then you can just start taking the top item and moving it to the end of the array, and then making whatever adjustments you have to. Okay, so we'll talk about that part in a second. The first step is turning this thing into a heap. Our strategy for doing that is going to be, we're going to, give me a second here. We're going to start with, I'm getting myself confused here. Give me a second. Is this right? Yeah, why am I? Okay, so we're basically going to start at the end of the array. So the 60, the 40, the 80, and go towards the beginning of the array, and make sure that each of those nodes is itself a heap. Okay, so we can skip over the 60 and the 40 and the 80 because they're leaf nodes, so we know they're going to be heaps, right? Anytime you have a single node, it's a heap. So we get up here to the 20, and we compare it with its two children. It's got a child that is bigger than it. So basically at that point, we're going to do the percolate down algorithm. Okay, so the first thing we're going to do is we're processing the 20, and we're going to percolate it down. So we're going to swap the 20 and the 60, right? Yeah, let me. Make sense? Okay, and so we just keep going backwards. The next node to consider is the 30. I'm on this one now. The next node to consider is the 30. It's going to percolate down, so I'm going to swap the 30 and the 80. Okay. The next node to consider is the 25. I'm going to percolate down, so I'm going to swap the 25 and the 80. Right? And then if the 30 or the 40 were, oh no, they are. So I'm going to continue percolating down. So now I'm going to swap the 25 and the 40. Okay. Now I have percolated down every node in the tree. So I'm done. Okay. What was the big O of that process? Creating a heap out of an array that's not currently a heap.
To go through every element, so it's n.
You have to go through every element.
More than once, actually.
But for each element, so each time you do an element, what's the worst case scenario of big O for doing one node? Log n, right?
Right. Log n.
No, because you got to do this for every node in the tree.
So it's n log.
It's n log n, right? So just right there, we've already got an n log n sort. We're already just as bad, I suppose you could say, as a quick sort or a merge sort. But that's just one step, and then we're done with that step. Then we have to do another step. So if that other step is also n log n or better, then the total big O is going to be n log n. Does that make sense? So if the rest of everything I need to do is still n log n, then my worst case scenario is n log n plus n log n, which is still just n log n. Okay, so here's the second part of the process. I'm gonna take this array, and each time through this process, I'm going to swap the first item in the array, which is always going to be the largest item in the array, with the last item in the portion of the array that is not yet sorted. Right? That terminology should sound kind of familiar, right? I probably use that phrase in many of the other sorts. That part of the array that is not yet sorted, right? So the first step is I'm going to swap the 80 and the 20. And when you do your assignment, I'm going to have you draw a picture, draw a new picture every time you do a swap. Okay. So the first step here is swap the 80 and the 20. Now I know the 80 is in the correct position, so I'm highlighting it in both the array and in the tree. And then I just have to deal with the fact that I just put a 20 here. How do I deal with that fact? Percolate down, right? So swap the 20 and the 60. And you'll notice I'm doing it over here in the array also. And then swap the 20 and the 80. Sorry, that was a trick question. I'm not going to swap the 20 and the 80 because the 80 is no longer in the part of the array that is not sorted. Right? So now I'm only dealing with indices 0 through 4. So when I swap the 20 and the 60, I get the 20 down here. There's nothing, the 20 does not have any children because I'm only considering up through the 25 to be part of the array, or that part of the array that is not yet sorted. So we're doing a max heap. So, well, no, we have a max heap. Now I'm converting the max heap not into any sort of heap. I'm just sorting those numbers. But so there's always going to be a portion of the array that is sorted at the end. And there's going to be a portion of the array that is not yet sorted, but I still have to make sure that part of the array is a heap.
So the 80s is down there because we already had a heap, and we knew that the root of the heap is the largest number, and so we can say that that's the largest number. It's going to be sorted, so we'll put it at the very end of the array.
Correct.
And now we don't have to deal with it anymore.
Correct.
Done.
So just to repeat that, you probably said it better than I could. But what we did was we knew that the root of the tree is the largest item in the tree. So we're going to swap that to the end. Now we no longer have to deal with it because we know it's in the correct position. But I mean, at this point, right after we swap to the 80 to the end, we no longer have to deal with the 80 because we know it's in the right position, but we still have to make sure the white part over here is still a valid heap. Otherwise, the rest of our algorithm is going to break down. So I need to, that number that I just put here at the root, I need to reheapify it down. So that's why I swapped the 20 and the 60. After I swap the 20 and the 60, I'm done because the 80 is not there anymore. Okay, so now you can see that all of if you just look at the white nodes, they are a heap. Okay, what's next?
Swap 60 and 25.
Swap the 60 and the 25, right?
60.
And 60 becomes part of the sorted list. So at this point, in my diagram, that should be highlighted. I don't know if I want to take the time to make that happen. On my Mac, I would just click a button up here. Anybody know what the trick?
I think you can right. You can highlight. It was the enable editing.
Say again?
There was a window that said enable editing. Oh, because this is a downloaded. Yeah. This is a downloaded Excel file. Okay.
Okay. So I'm not going to do that right now.
Yeah.
So just imagine that I highlighted. I do it in the next round, but I should have highlighted the 60 here. Okay. So now we have the 60 and the 80 are sorted, and then 20. These 4 over here are the part of the array that is not yet sorted. Those are supposed to be a heap. They're not currently, so I need to reheapify the 25 down. So I'm going to swap the 25 and the 40. Now I decided to highlight the 60. Then I'm going to swap the 25 and the 30. So now I'm back to the point where all of the white nodes make a heap. there's a verb there that I can't quite remember. They constitute a heap. All right, everyone okay so far? Now just keep going, right? Now swap the 40 with the 25. Okay, now reheapify the 25. So swap the 25 and the 30. Now the white nodes constitute a heap.
Isn't it possible that when you move the 30 from the left subtree to the root, that it's still not a heap? Because couldn't the 20 have been 40?
No. Because we started off with it being a heap.
Every time you percolate, you pick the largest child.
Yeah.
So that's always going to go. The largest child is always going to go up.
Yeah.
Right, out of the two.
Yeah.
This can't be a 40 because it wouldn't be a heap because the 25 is here.
Yeah. Okay.
Is the definition of a heap that it is a tree with the largest at the root and every child is smaller?
Every child is smaller than its parent.
Okay.
Yeah.
So it's not a BST tree.
Correct.
Okay.
It's not a binary search tree.
Okay.
Right. So, I mean, I have to admit that I'm not sure I can 100% clearly explain why that will never happen.
You're right.
But I know it won't.
Yeah, there would never be a 40 on the right under the 25. Because
I think you're right. Yeah. Yeah. Right. Yeah.
Yeah, I think I'm right.
Whatever's over. Anyway. Okay. Okay. So what did we just do? We just swapped the 25 and the 30. So now we have the white nodes constitute a heap. So we're going to swap the 30 with the 20. And now this should be highlighted, right? The 30 should be highlighted because it's now part of the sorted part of the array. And I need to heapify down the 20. So I'm going to swap the 20 and the 25. Okay. Now it's kind of funny because my array is sorted here, right? But the algorithm doesn't have any way to check that. I just keep going. And I swap the 25 and the 20 to make it back into a heap, to make the white nodes back into a heap. Then I swap the 25 with the last element of the not yet sorted array. So I'm swapping them back again. But this time, the 25 is considered part of the sorted part of the array. And at that point, I'm done because I only have one element left that's not sorted. Okay. Any questions about that process? It's not too bad. It's not, I mean, in my mind anyway, it's way easier than the balanced trees that we talked about last week. And I don't know, it's kind of fun.
So we said that was an operation of n log n.
Yes, the total time is in log n. Okay, I have to do n log n to get it into a heap. And then this part down here is whatever it is I'm doing it n times, right? And what I'm doing n times is swap two things and then percolate down. So each time I do this, it's log n. So n log n. So you could think of it as n log n plus n log n, right? N log n to create the heap, to turn the array into a heap, and then n log n to do the sorting. So let me just bring up, is this going to work? Just because we have a couple minutes left, if you guys don't mind. I think it's pretty enlightening to just be able to play around with timing these things. So if you recall back in the sorting unit, I provided this sort.cpp function, and it had a heap sort in it. We hadn't covered heap sort at the time, but it was there. So you can see you can see some code here for it. Here's my heap sort. First convert to a heap, and then while the number in the unsorted part of the array is greater than 1, subtract 1 from num unsorted, swap list of 0 with the last item that is still unsorted, and then reheapify down. Right? Here's convert to heap. We did that. And here's reheapify down. We won't go into a lot of detail about that. But yeah, I'll leave it at that. But in terms of like timing this thing, give me just like 2 minutes to see if I can get this set up so we can actually see it run. Okay, so here's my constants. I need to set the system to Windows. I'm not going to print the values because there's going to be too many of them. I'm going to use really big numbers, and I'm going to make the size of my array 50,000. I could probably make it bigger, but let's start with that anyway. And I'm just going to run this thing, and it's going to tell me how long each different algorithm takes, right? Hopefully the slow ones won't take too long, right? I think this is a pretty darn old computer now. So 50,000 items. Bubble sort is an n-squared sorting algorithm. So it's doing 50,000 times 50,000 swaps. So what's that? 25 with 8 zeros after it. So 250 million swaps. And it's taking it about 10 seconds. So apparently it's doing 25 million swaps per second. I mean, just speaking very roughly, right? It's doing a lot of other stuff too, but the swapping is probably what's taking most of the time. And you can see that the bubble sorts are all taking a few seconds each, and then the n-log n sorts are essentially instantaneous, right? Like no comparison. So the heap sort, you can see it's slower than quick sort. So in a general, for a general situation, if you have to decide which sort to use, you'd probably use quick sort, not heap sort, unless you had some special reason to use heap sort. I mean, I suppose, no, that's not even true. Never mind. And then, but it's significantly faster than merge sort, right? And again, this is just one run on one system. I think last time I ran it on my system, merge sort was not that much slower than heap sort, right? In this case, it looks like it's 10 times slower. But I don't think typically it would be that much slower. And then the other thing that's always weird when I do this, and I'm not quite sure I might have talked about this when we talked about this the first time, but whenever I do this, selection sort always shows up as being like taking 1/3 the time of the bubble sort. Yeah, maybe that's not too as far off as I was thinking it was, but anyway, so just a chance to sort of give you a sense for how much faster, for where heap sort fits into the mixer. Good. All right, I think that's all I have to say about heaps. Anything else we should talk about?
We use that Like is that kind of what heaps are used for mostly? It's just sorting.
So the question is, what are heaps mostly used for? I would say no, not really for sorting, because if you're going to sort, you would just use quicksort. So typically, the main use of heaps is when you're implementing a priority queue. That kind of makes sense because you've always got the biggest item right at the top. And anything else that you use to implement a priority queue is going to take a lot longer to rearrange once you take out that largest item,
right?
Or longer to find the largest item, right? In a binary search tree, you can find the largest item in average case log n, worst case n. In a heap, finding the largest item is constant, big O 1, right? So, all right. You guys, let me, I just had it.